semester. Yeah, just about 1 month. Yeah, let's say mainly April. Yeah, because we will do final at the end of this month. So basically, we can only use the remaining time, approximately 1 month, to here to give you chances to fix the problems in midterms. Then you can get a maximum possible points recovered. Yeah, that's the main idea. Yeah. Now let me tell you the details. How do I plan to do? Not today, not starting from today, starting from Thursday. Thursday we will start to do the recovering steps. Yeah, recovering. Yeah. Let me give you the detail. Yeah. All right. All right. So we only target the midterm Part B questions, 15 questions. That's our target. Okay. So target. If you lose any points, you have chance to recover. Yeah, that's the goal. Actually, the goal is let you learn how to solve all those questions independently. That's our goal. Yeah. Because the reason when I graded your homework assignment 1 and 2, overall, you did quite well. Homework 1 average 84 plus. Homework 2, 83 plus. Yeah, that's quite good. Yeah. But you can estimate our midterm much lower than that, right? Yeah. I haven't graded, but midterm much lower than that. Okay? Yeah. So that's when I set my goal, because my goal, I want you, all of you in this class, you can solve those basic questions. Here I treat the midterm, that 15 questions, the basic questions. So all of you can solve those basic questions after you finish this class. That's my goal. Okay? Yeah. Yeah, because if you look at your textbook, Part A, that's the basic part. That's just the coverage of our midterm. All right? Yeah. So here, I want to do the final push for those students who cannot solve those questions independently. During this month, I'll give you plenty of chances to practice and recover the points. How about that? Yeah. The detail, the execution. Let me give you the someone. Yeah. Let me. Yeah. All right. So the goal. Now you know the goal, but how do we do it? Yeah. First, we cannot use our regular class time because we do not have that much time. So we cannot do in our regular class time. It must be after the class. Yeah. Or I can finish 5 minutes earlier. Yeah. That much time. Yeah. After the class. And all of you, if you want to recover, because some of the students, you get a full credit, then you can leave. Yeah. So each day we only do 1 or 2 questions. Okay, 1 or 2 questions. I project, I display those 2 questions on screen. Yeah. For those students who want to recover the points, if you lose points in 1 of the 2 questions, you can, get a piece of paper, you copy the questions on your paper, then you write the solution. When you write the solution, you cannot see anything, okay? You cannot see computer, you cannot see textbook, you cannot see notes. You have to solve directly from your mind. How about that? In that way, I treat you so you can do it independently. That's my definition. You can solve it independently, okay? Yeah. But you can practice at home. Yeah. I will post the solution. I post the solution to all those 15 questions. Yeah. Early tomorrow morning, I post all solutions to all 15 questions tomorrow morning. You can study. But I will tell you on Thursday, what 2 questions? Thursday, we only do, let's say, first 2 questions. First 2. Because I do not want to use too much time after the class. First 2 questions, you practice, try to understand, use my solutions, try to understand, practice at home, okay? Then, Thursday, at the end of the class, then you can work on a piece of paper. You can do 1 or 2. Yeah, I will keep track of it. So if you can solve it independently, I give you half of the losing points back immediately. Okay? If you can solve independently. So our definition in class here, and not remote, not at home, must be in classroom. If you can do it in front of me without using your notes, computers, textbook, you just write your solution. Okay? That's my definition. You can do it. Then I'll give you half of points immediately. Question, Jenny?
Are they going to be as difficult?
Same type of questions. But I modify some numbers. I change some numbers. Basically the same. Exactly. I do not change too much. I just use the same type of question, but I change a few numbers. That way. Okay? Yeah.
So the numbers will be different, but the structures of the equations that we got wrong will stay the same.
Structure? Well, the number, yeah. Your solution correct. If you mean only the final answer, not slightly different, right? Yeah, that only 1 point. You lost 1 point, but I treat you, you pass it. Yeah. In that case, I treat so you pass it. Yeah.
Well, no, I think he's asking that the questions that you're going to display. He's asking, so you're going to give us the solutions.
Yeah.
Will those questions that you display have the same structure as the solutions, but a different answer?
Yes. Different answers.
Okay.
The same structure. Yeah. Yeah. Right. So my solution, just our original midterm questions. Okay. Yeah. But when I display, I change a few numbers. How about coefficient? Right. I only change a few coefficient numbers. Yeah. So that means you cannot just based on you try to memorize, directly. You have to understand it. Okay. So you have to understand that you need to do calculation, right? Because I changed the coefficients. You need to do calculation. You cannot just, try to memorize our solution. That's not good. Yeah. So I do not treat. So you can do it. If I change coefficients, I will not change conditions significantly. Yeah. You won't see, I change some main condition. No. You won't see the main condition will be changed. Yeah. Only change numbers. Yeah.
Will we get our tests back prior to this happening so we can see which ones we've missed so we know which ones we have to pick up?
Test back. Yeah. Thursday, I can give a test back. Thursday, you can take a look. But Thursday, when you do it, you have to close everything. Okay? But I post the solution. We only do first 2 problems on Thursday. Okay? Remaining problems, next Tuesday, another 2. Next Thursday, another 2. So after each class, we recover 2 of them. How about that? Yeah. Each class, we work. Okay? So here, I give you a chance. So you need to pay the effort to recover, right? So it's not free points, right? You have to do a lot of work. So I want to use this final chance to push push you to make sure you are able to solve all those basic questions. 15 I treat as basic questions after this class. Okay? Or I treat it as a training session. So if you can pass the training session or not. Yeah. All right? Yeah. And yeah, but that's only half points, half of the losing points, only half. Yeah. I even think of give you another chance to recover the remaining half in the final. In the final, if you can still solve, still I changed a few numbers. Final, we have normal questions. Yeah, but after normal questions, if you can still recover some of the questions. Yeah, let me see. Yeah, how do I do in final? Yeah.
So you're saying the final will have, let's say, 1 through 10 completely different questions based on the material that we're learning now.
Right.
And then like what, 11 through 15 are like bonus questions based on the material that we have already learned, like from this midterm? Is that what you're saying?
No, final actually, final I mainly want to test new materials. Yeah. Old materials I do not want to test. Yeah. So I only give you questions for the new materials. Yeah. But here I'm thinking about some way, some possibility. Yeah, because this midterm, most of you, after you try very hard, you can only get 50% points back, right? Losing points. So here I want to see if in a final I can give you some more points back. But you need to show me again in the final, you can also do that in the final. Then I give you the remaining missing points back. So that you pretty much, you can recover almost all points of the midterm back. So that's what I'm thinking. Yeah, but you need to pay a lot of effort. Okay, basically you need to solve all those 15 questions. Yeah. Yeah.
I don't know if everybody would agree, but I guess I know talking with other students after the test, the exam was very difficult to even finish in 2 hours. I don't know if this would be feasible for the final to do something. I don't know if it has to be take home, just something modified, because if they're going to be as difficult as those problems were, to expect us to do those in 2 hours, which would be 12 minutes per problem, I think was unreasonable.
Yeah.
And I don't know what to propose instead, but I think I personally was confident going into the test that I can figure out these problems, but I felt it was unreasonable to be able to solve all those problems 12 minutes per problem. Because one of them took me 12 minutes, and then another one, I didn't even know we had to study for circuits for the test, and I was spent 12 minutes trying to research what the equation was. So I don't know. So that's kind of how I feel.
Yeah, here, when you prepare, do you follow because I gave the list of 15 questions, so do you go through, prepare all those 15 questions, right?
Well, I mean,
Yeah, but
personally speaking,
Yeah.
I prepared 10 through, what was it, 10 through 20, I believe
Yeah.
you gave us.
Right.
But I didn't worry about 21 through 25, which the circuit problems were in the 21 through 25.
Yeah, I remember in the review session I said this. The last 3 word problems, one pick from module 1, one pick from module 2, one pick from module 3. Yeah, so I use that. So that it may not be the order, through 20. So then the order may change because I pick one from each module. Yeah. And I even talk about the possible questions. Yeah, a little bit. Yeah. What Max said, if those are new questions, then I give you 10 in 2 hours. Then it's not reasonable. Then I agree. But they are not new questions, right? and you practice in homework assignments, then review, and you know specific question types. Why still so hard in the test?
Because
Is too much pressure, right?
no, it's not too much pressure. The problems take forever. If I'm doing if I have to do integral and then integration by parts and then integration by parts again, or I have to do variation parameters where I have to figure out. The process takes a while to take derivative, plug it back in, figure out the homogeneous, and like. I don't think it's.
It was because like I was left with the impression like the homework problems are going to be hard, and I expect that the homework problems should be more difficult.
Right.
But then I get on the test, and some of those integrate. It was almost like you picked out the hardest ones out of.
Oh, I said exactly what I will do in the review.
I understand that.
Yeah.
But whenever it comes to, okay, you want us to have 15 done within this 2-hour time period, even for me, it took me 2.5 hours.
Yeah, yes.
So, maybe, and whenever you're doing integration by parts twice, say if you don't do it correctly the first time, you pick the 2 variables in the wrong spots, then you have to go back and try to find your mistake, and that was a big part of it.
Yeah. Yeah,
So I think
right.
I was expecting every single thing that you had
Mhm.
on the review, and they
Yep.
were on there, but they
Yep.
were the harder ones instead of just picking ones that could have been not necessarily, maybe a little simpler that would still be able to let you see that we understood the concept and that we could apply it to those problems, if that makes sense.
All right.
I'll say that sometimes the questions we got don't necessarily reflect what questions we worked on in the class and also in the homework.
I think that, the other struggle I had was with the circuit problem. I thought we had talked that we were following directly what the review said. So then, okay, I look at this and then I see the word problems that will be on the test were radiocarbon dating, heating, office building, mixing problem. And then we get to the exam, there's a circuit one, which I hadn't studied because I thought I was going to get take home, so I was going to study it because I was studying homework 2 and then I was studying for the test, so I wasn't taking long.
Yeah.
And then there was also a 2-tank, which is still a mixing problem, but by the view it looked like that was on the take-home. So I guess it was unclear, and so I guess that was another frustration. I guess that's kind of what Kevin was mentioning. But I'm agreeing with what Jenny was saying. I'm not trying to say you should hand it to us and give us an A. I'm not saying that. I also personally work slower than other people, so the take home helps me to be able to work through everything as much time as I need. But I also know that changes how you.
All right. So here, the 10 questions in the midterm actually checking your study results. Yeah. Actually, so we prepare so long that I want to see if you can do the questions we have practiced here in 2 hours. Yeah, that's take integration by parts takes a lot of time, but we may not have too many, right? Yeah, we may have 1 or 2. I do not count. Yeah, small number. Yeah, so small number. You try to manage your time. Yeah, and for the electric circuit problem, basically I just change numbers. Yeah, I look at that. Yeah, we can find our old example. Yeah, difference just the numbers. Yeah. So if you find old solution, you use the old solutions, you can solve it. Even you do not prepare it. Because you follow the old solutions.
But just taking that's what I was initially saying.
Right.
I took all that time that I could be putting on another problem.
Yeah.
Just to search for it.
Yeah. Anyway, because we are at this point, right? We're already at this point. So the remaining semester, I just want to implement the idea I talk about. Yeah. Yeah. So you prepare based on that. How about that? Yeah, prepare. Yeah, based on that. So on Thursday, I will display the first 2 questions on screen. Yeah. Yeah. For some of you who already, yeah, so I will give you test paper back. So if you feel you already get the points, so you can leave. Yeah. You do not need to do that. Only you lose the points greater or equal to 2. Then you can do recovery. Yeah. If 1 point, so that's the minor problem, so then you do not do it. Okay? Yeah, 1 point. At least 2 points, you do it. Yeah. All right? Oh, all right, yeah, so let's do it in that way. Yeah. Okay? Yeah. But at the end, I want to make sure everyone in this class, you can solve those basic questions independently. Yeah. That goal should not be very hard to reach, right? Yeah. Yeah. Okay? Yeah. Then, before each class, I will announce in the Canvas, let you know what are those 2 questions. So you can do preparation at home. Okay? Yeah. Yeah. So I want to see the result. Yeah. After we do this kind of, study, so if you can do better. If you can do better. Okay? All right. Yeah, I may do this way. So, yeah, because you talk about the time. Yeah. I know the time limited. Time limited. Yeah. All right. So then, yeah, because I need to find a fair way. First, fair way. Second, give you plenty of chances. Yeah. And so the final I may do in this way. Okay. Yeah. Still, the basic format similar to the midterm. Similar to midterm. Yeah. 2 hours. Okay. 2 hours. Yeah. Then I cut 10 questions, 2 hours. Final. But I cut off immediately at 2 hours. I stop. Okay? Then, after that, I give you half an hour, 30 minutes for recovering the midterm missing points. Only 30 minutes. How much you can do, whatever you can do. If you cannot finish, I just give you a last chance to recover the missing points of the midterm. How about that? Only 30 minutes. Because before that, you already recover a lot, right? Yeah. So the last chance, yeah, only 30 minutes. Yeah, give you a final chance to recover. How about that? Yeah. Although it's not easy, but for you, you have another chance to improve. In this way, we do not mess up the midterm and the final. Otherwise, if we mix them, it's not good. So here we do not mix. 2 hours, we switch to midterm recovery, the final stage. That's something I can let you do it in the final. Okay? Yeah. All right. Yeah. So let's already half an hour. Yeah. Let's do the continuation part C. Yeah. If you can give me feedback, that's good. If you feel you have better idea, you can let me know. Yeah. First, we practice our, first round recovery. Yeah. Then the final, that's our last round recovery. Okay. Yeah. Yeah. But for me, if I do in this way, at least I can make sure most of our students, I hope 90-something%, at least you can do those 15 basic questions, right? After you finish this class, at least you can do those 15 basic questions. Yeah. Yeah. All right? Yeah. Okay. All right. So let's focus on the new material. This Laplace transform, we already, so here, we already did the introduction part, the first 7 slides. We already did it. Okay? Yeah. So now let me jump to after the slide number 7. Yeah. The 7th slide, this one, we did one example. Here, I just remind you, we did one example here. Given a function, if we know its Laplace transform, then we use the properties. Here, I give you the properties. Then we use these properties. We can calculate the original function. Yeah. So that's the example before the midterm. All right. Now let's continue. Now we want to use Laplace transform to solve ODEs. Yeah. So you will see very powerful. Yeah. Very powerful. Yeah. All right. So let me continue. Yeah. Yeah. Actually, we did this one. Let's move to the next slide. Yeah. Here. All right. Derivative. Oh, not this one. Yeah. C.2. Existence and uniqueness. Yeah. Before we do the computation, this theoretical result, I like you to know it. All right. Yeah. So unique existence, uniqueness. We haven't talked about. How do you know the Laplace transform of a given function exists? How do you know it? It may not exist. Yeah. Here, there is a simple condition we can check to see if it exists. Where is my... Here. All right. Yeah. All right. Yeah. Existence theorem. Here, I only give you the result. Yeah. One simple condition. Why we need to know existence of a transform of a function? Yeah. Yeah. Because if you know it exists, then you have confidence, right? Otherwise, when you do a lot of calculation, but it's garbage. It does not exist. Yeah. All right. So it's important. After we find here, but for solving ODE, actually, this question is not that big. Yeah. The reason is, even if we do not check existence or not, after we find a solution, we can verify it, right? We do not need to check Laplace transform, exists or not. We just verify the final solution. We know it's the correct one. Yeah. So that means the existence step may not be that important. Yeah. All right. So we can verify to see if the solution is valid, but it helps us to understand Laplace transform better. Yeah. So we want to know it. Yeah. All right. Here, the theorem. Yeah, let me explain this theorem. Existence theorem for Laplace transform. Yeah. First, let's look at the condition part. Yeah. If f of t is defined and piecewise continuous. Piecewise continuous. So the function can be broken into a few pieces. Each piece is continuous. That's good enough. Yeah. We know if f is piecewise continuous, then its integral exists. Yeah. Yeah. If you take integral on any interval, it exists. Yeah. All right. On every finite interval, all right? Yeah. On the semi-axis here, we consider semi-axis t greater or equal to 0. Yeah. Only the positive side. Yeah. We do not look at the negative side, only positive side. Yeah. Because the Laplace transform is defined on this semi-axis, positive side. Yeah. If you look at the definition of Laplace transform, all right, that satisfies 2, yeah, I should give you the 2, all right. Yeah, so this is piecewise continuous, the figure. Yeah, all right. Yeah, I will, yeah, 2 is here, okay? Number 2, inequality. Absolute value of the function f of t less than equal to capital M, some constant, some bound, constant number, positive constant number, then times e function, e to the k, k is some parameter, k number, okay? Yeah. So if we have that condition for m and k, some constant m and k, then Laplace transform L of k of f exists for all s greater than k. That's the condition. Okay? It can be proved. The proof is not that hard. Okay? Yeah. So here the proof. Yeah. We just look at the, from the definition of Laplace transform. We estimate its integral from 0 to infinity. Yeah. Let's do estimate. Okay? Yeah. Inside. Yeah. Yeah. E function positive, so we can take it out of the absolute value. Yeah. So here we only need to estimate this absolute value of f function. We use this inequality. Okay? Give it inequality. All right. So then we, replace absolute value term by this e function. Then we can calculate. Yeah. So the integral result m over s minus k, where s greater than k, so this number is a valid one, meaningful, okay? Yeah. So the integral of Laplace transform is well defined. Yeah. It exists. Yeah. Here, later, if you want to see if the Laplace transform of a function exists or not, you only need to check this condition, okay? This inequality. Yeah. Yeah. And this bound function, it's an e function. Actually, the function here, if the function is not too bad, the increasing rate is not higher than e to the kt, then you're fine, okay? Then you can calculate Laplace transform. Yeah. But, if you're looking at a function like e to the t squared, then you have trouble, right? Yeah. Because it's too high. The increasing, too high. Yeah. If you calculate Laplace transform, it does not exist. T squared. Yeah. Here we only allow kt. K, you can choose any constant k. But the t part, if its order higher than t, you have problem. Yeah. Even not t squared, t to the 1.1, you have trouble, right? T point 1.1, higher than 1, you have problem. Yeah. All right, so that's this theorem. Yeah. All right. Then uniqueness, yeah, after we have the existence part, then uniqueness. If two continuous functions have the same transform, yeah. Here, when we talk about uniqueness, we require the function slightly, tougher. So we impose the condition, stricter. Two continuous functions, not piecewise continuous, must be continuous. Yeah. If we consider two continuous functions, if they have the same Laplace transform, then those two functions must be identical. That's the uniqueness part. Yeah. All right. Yeah, so here just some theoretical result for you to help your understanding. Yeah. Okay? Yeah. In our computation, we may not need that. Yeah. But for your understanding, you need it. Yeah. All right. Next, C.3, Laplace transform of derivatives. Yeah. Because when we solve ODEs, we have a lot of derivatives. Now, we want to apply Laplace transforms on the derivatives. Okay? All right. Yeah, here. Point of view of operational calculus. Yeah, here, I mentioned this operational calculus before. Do you know what's the meaning? Yeah. Here, let me recall a little bit. Yeah. When we do calculus, we need to take derivatives, integrals, right? That's the typical operations we take in calculus. Yeah. But here, it tells you there is one special way by applying Laplace transform. We can change the typical calculus operations to algebra operations, algebraic operations. That means you won't see derivatives, you won't see integrals, you just see multiplications and divisions. Much easier than calculus, right? Algebraic way, much simpler than calculus way, right? Yeah. So we will see that power. That's the reason why Laplace transform is so powerful, because it can make that switch. Yeah. That change is big. Yeah. All right. Operations of calculus on functions are replaced by operations of algebra on transforms. That's the main idea. Yeah. All right. Yeah. So here, let's look at the derivative. Here, I show you the derivative result. Yeah. Later, you need to use this theorem to solve your ODEs. Mainly, these two formulas. These two formulas critical. Okay? Later, you need to use these two formulas again and again. Okay? Yeah, to solve ODEs. Yeah. All right. Here, the transform of first, second derivative of f of t. Here, the formula given. Yeah. So we can derive easily. Yeah. Yeah. So here. All right. So then, a lot of conditions. Yeah. Yeah. So here we assume all the conditions are satisfied. Yeah. So although, a lot of descriptions on the conditions. Yeah. But because our functions are good enough. Yeah. We just assume our functions are good enough. So we don't worry about all these conditions. Yeah. All right. Then, with these two formulas, now you can see left-hand side of the equality related to derivatives, right? Differentiation. But after we apply the Laplace transform, the right-hand side, you do not see derivatives, right? The right-hand side derivatives are gone. Right-hand side derivatives are replaced by multiplications. First derivative is replaced by s times Laplace transform of original function f. Second derivative here replaced by s squared times Laplace transform of the original function. Okay? How good it is. Right? Yeah? Yeah. Your integration by parts will be gone. Yeah. Later you will see, integration replaced by division. Yeah, because differentiation replaced by multiplication. Integration, just a reverse process, right? Reverse process of differentiation. What is the reverse process of multiplication? Division. Yeah. So integration is replaced by division. Yeah. Much simpler. Yeah. All right. Proof of the derivative form. Yeah. Just simple calculation. Yeah. Not too long, not too hard. We treat as a practice. let's practice. Okay, all right. Yeah. So these two formulas. Let's calculate the first one. Yeah. The first one, integration by parts. Yeah, here you need to do it, integration by parts. Yeah. But the first term, very easy, you can get a 0. Oh, not 0. F of 0 times 1. Yeah, f of 0 left. Yeah, f of 0. Infinity, 0, because this negative st, s greater than 0, this e term make it the limit 0. Yeah, infinity, the limit is 0. Okay? All right. So then the second term, this is Laplace transform. S times Laplace transform. Yeah, that's the formula. All right. Now let's calculate second derivative Laplace transform. Yeah. Second derivative, can we apply the first formula? Yeah. Because f double prime is the derivative of f prime. We already have the derivative formula. Let us just apply our first derivative formula. And inside this term, we can apply that formula another time, right? Yeah? Another time, this bracket, we apply that derivative formula the second time. Yeah. After simplification, we get this expression. Simple. Yeah. So these two formulas, not very long, so we can prove it in the simple way. Yeah. But when we apply them to solve ODEs, so you will see very powerful. Yeah. So the computation is not as hard as our old way. Old way, you feel it's hard. Yeah. Yeah. Because you cannot complete in 12 minutes. Right? Yeah. Here, let's see. Oh, before we solve the concrete examples, let us look at the higher order version. Yeah. Because you can apply these formulas again and again, right? Yeah. Yeah. Then we have the higher order version. Yeah. Yeah. Just do iterations. Yeah. You only need to do iterations. Yeah. All right. Yeah. After a few times, the last one, so this is the theorem, gives you the final solutions. Yeah. So for any higher order ODE, you can apply this formula to get its Laplace transform. Yeah. And you can convert the given ODE to an algebraic equation. Algebraic equation, okay? Or multiplications here. Oh, yeah. So the derivative values, you only use the initial conditions. Yeah. Here, at 0, initial conditions. Yeah. All right. Yeah. So that's our theoretical preparation. Yeah. Yeah. Calculate Laplace transform by derivative formulas. All right. Let's do some calculation. First, f of t equals t times sine omega t. Yeah. All right. Let's calculate Laplace transform of f. Yeah. Okay. All right. Here, by definition, there is one way. Yeah. You will see by definition, you need to do a lot of work. Here, I couldn't complete. I just show you a few steps because it's hard for me to complete it by definition. All right, so when we start, this is the definition of Laplace transform. But we need to do integration by parts, right? Yeah, so that's the part, takes a lot of time. We do preparation, integration by parts. The first time integration by parts, although this part is gone. Yeah. The good thing is this first term, after we, plug in the upper limit, lower limit, the whole term is gone. Yeah. Yeah. All right. Yeah. But the second part still relatively hard, right? Yeah, two terms, two functions. You may need to do iterations. All right. So here I leave it here. Yeah, we know it's relatively hard. So I leave there. Now I want to calculate Laplace transform. Without using definition, let's apply our derivative formulas. How about that? Derivative formulas. Yeah. All right. First, Laplace transform of f double prime, this double prime, equals that, this formula. Let's use this formula, okay? All right. F of 0, easy to see, initial value. F prime of t, this one, plugging 0 there. F prime of 0, also 0. Okay? Also 0. Yeah. All right. Yeah, so we're ready. You can see these two 0 values make the last two terms gone. Okay? Much simpler. Yeah, last two terms all disappear. Okay? So we have a simplified version. Laplace transform of f double prime just s squared times its Laplace transform. How about that? Okay? Yeah. All right. Now let's calculate the double prime Laplace transform. Yeah. Calculate the double prime function first. Then let us calculate Laplace transform. Okay? All right. When we calculate Laplace transform, here we use the existing formula. Cosine omega t Laplace transform, our formula number 7. Yeah, here, I copy the formula number 7. Number 7 in our table. We have a table. Okay? Yeah, here, I copy that formula from that table. Number 7. It's this one. And, yeah. So there, all right. Based on this formula, s squared times, yeah, because f, all right. Yeah, so here, yeah. So omega squared, all right. What's, all right. Laplace, yeah, 2 omega, this, yeah, yes, then squared, f, right? Yeah. So here, s squared times that, right? Yeah. So, yeah. Here we do some simplification. We can get that. Yeah. So here, yeah. Yeah, did I? Oh yeah. 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 So, all right. So, yeah. Here you can see that. Yeah. Let me show you. See that. All right. The left-hand side, we just apply Laplace transform directly to get the left-hand side. Okay? Yeah. By linearity principle, linearity property or principle. Okay? 2 omega here, that's the 2 omega here. Okay? Yeah. Then Laplace transform of this cosine omega t, that's this one. So you have this part. Okay? All right. Second part, omega square, that's the omega square here. Okay? Then the remaining, that's our original f. So you have Laplace of f. Okay? Yeah. Left-hand side, we just directly apply on this expression. Then by linearity property and also by our formula number 7 together. So we get this form. Right-hand side, just apply this one. S squared times that formula. Okay? Yeah. Here you can see this equation, only this Laplace transform is unknown. The remaining known, we can solve for L of f. Yeah. So we find L of f equals this number, Laplace transform. Now you can see this computation this way much simpler than our older way, right? Yeah. So you can see, because we only need to do solve algebraic equation. We do not need to do, derivatives, integrals, like we usually doing here. Okay? Yeah. Yeah. So this is one example. Okay? One example. All right. But you need to use all these basic formulas again and again. Okay? All these are the basic formulas. Yeah. So, yeah. All right. C.4. Laplace transform of integrals. Now, let's do integrals. All right. Integral, reverse process of derivatives. Yeah. So not very hard. Yeah. For differentiation and integration, reverse operation each other. Similarly, multiplication and division, reverse operation each other. Okay, yeah. So with this simple view, now let's look at the integral. So let the g function be integral of f function. Now we want to look at the, here. Yeah. So the derivative, we can write the equivalent form. Yeah. So then, yeah, existence. Yeah. So, before we apply Laplace transform, let's check the existence condition for the integral one, g, for the g one. Okay, yeah. This is the general condition, yeah. And here we want to check the g function. It's an integral of f if it has the same property. Okay, all right, yeah. So let us just replace. Yeah, because f, we know it has that condition. Yeah, we just replace the absolute value of f by its upper bound. This is its upper bound function. Okay? Yeah, so we can calculate it, get this one, minus 1, minor term, we just ignore the minus 1. All right? Yeah, less than or equal to that one. And this function, this form, you can see has the same format of that one. Okay, the same format. Yeah. Just the constant we changed slightly. Okay, we changed the constant slightly, but this inequality tells us the Laplace transform of this g function also exists. Okay, yeah. So we can apply Laplace transform on it. Yeah. All right. For the derivative formula, we already have the derivative formula, right? Yeah. Let's apply our derivative formula. Okay? This is g of 0 based on the definition. G of 0 is 0, right? You make t 0. Okay? Upper limit 0. 0, 0. G of 0 is 0. So this last term is gone. Okay? This last term is gone. All right? Yeah. So it's even simpler. S times Laplace transform of g function. Even simpler. Now you look at the relationship between these two Laplace transforms, multiplication of s. Yeah. But if we look at the other way, yeah, because this is integral, this is a g function. This is a g function. Laplace transform of this g function equals division operation. Okay? The Laplace transform of f function, then you do divided by s. Division, not multiplication. Okay? Yeah. Reciprocal multiplication. Yeah. Or if you use the inverse Laplace transform, you can write that way. Okay? Sometimes you need to use the inverse transform. Okay? Yeah. So here you can see we can use inverse Laplace transform to calculate the integral of f function. How about that? Yeah. Yeah. And one way you can calculate the f function, but you need to know its Laplace transform first. Okay. All right. So that's a formula. And later, when we need it, we will use these formulas. All right. So let's take a break.